Welcome to our series, Science and Society, Making Sense of the World Around Us. My name is Rebecca Lowe. I'm the Adult Program Coordinator at the Lewis Public Library. This lecture series is co-organized and moderated by Fred Dilla and Linda Dilla, and also Colin Norman. So Fred, I'm going to turn it over to you for the introduction. Thank you.
Thank you, Rebecca. We're very pleased to have back to this series our good friend John Mather. Some of you who know our series may recall John's talk 2 years ago about the Webb telescope that had just recently been launched, and the first pictures were coming in. And we're pleased to have John back 2 years later to talk about the wealth of data that has been coming from the Webb telescope. So I want to turn it over to our good friend John Mather, who will discuss the infrared treasure chest from the James Webb Space Telescope. John?
Yes, thank you very much for that lovely introduction. I'm delighted to be back after a couple of years because we found out a lot of new things. So I will repeat some of the old information, but some is brand new. So on the front page here, you see our great telescope as we imagine it to be in outer space. The great golden hexagon is 6.5 meters across. It's protected by a sunshade as large as a tennis court. It was launched on Christmas morning, 2021. It's now been in space for 1,000 days and it's working so beautifully. We are thrilled. We're expecting it to run at least 20 more years. So let's look at the next slide. Where did we come from? I think I wanted to know this when I was 6 years old. And it's getting harder to understand what we actually mean because we are hypersocial creatures communicating with each other in so incredibly many different ways, from speech to chemical to touch, and to say nothing of computers. Are we alone? Well, our perspective on this has changed immensely since not so very long ago. It used to be that people thought life required a miracle, or at least an extremely unlikely coincidence of physical situations. And now I think at least many scientists have flipped over to the other side to say, well, it probably happens wherever it's given a chance, and maybe quickly. On the other hand, intelligent life here on Earth took the entire history of the universe, 13.8 billion years to get here. So a big question, and we will not be able to tell you that answer. Next slide. So the we that is here is actually constructed in an incredibly complex world based on the growth of information. There's a lovely book by Stuart Kauffman called A World Beyond Physics, where he tells us this story. And by the way, no, there is not another you on another planet. The universe is probably infinite, but the infinity of combinations of things is even bigger than that. As you know, there are many different kinds of infinities. So we are here because of our genetics, our environment, and an incredibly complex world that we are in, and it's incomprehensible. And I'm pleased to say that it is incomprehensible. So let's look at the next slide. So back in 1929, Edwin Hubble drew us this graph, showed us that the universe is expanding. Distant objects are going away from us with a speed proportional to distance. These are little dots represent galaxies. And divide the distance by the speed, you get the age of the universe. It's the first time we ever knew there was an age of the universe at all. Although it had been predicted by George Lemaitre based on Einstein's equations, it was still a big surprise to most people, including Einstein, who believed this could not possibly be correct. Here we show on this slide the Cosmic Background Explorer satellite, which was built to measure the cosmic heat that we observed with the Cosmic Background Explorer satellite. Was my thesis project grown up to cosmic proportions. This satellite was launched in 1989, and it measured the cosmic heat with extraordinary precision. So now we know that what we call the Big Bang Theory, should more properly be called the expanding universe story, is probably correct in many, many details. We even have now what we call a standard model which includes all of the, well, it includes 7 parameters for dark matter, dark energy, the original temperature, and the matter density, and all kinds of other things that it takes to describe the sky that we see, and it fits. Although there has been trouble in paradise recently because we have more than one way to measure the rate of expansion of the universe. And they are getting to be slightly different, and at least from the perspective of statistics, they're significantly different. So we have a new mystery now. Next slide, please. Here is the map that we made when we've got the COBE satellite up, the sky as it would be seen if you could see wavelengths of a millimeter. The hot and cold spots there represent temperature variations of a part in 100,000 in the cosmic heat. And it turns out that's just enough that we can exist. When Stephen Hawking saw this pattern, he said that's the most important scientific discovery of the century, if not of all time, because, I suppose, he was thinking, this tells us how we got here. If those spots were not there, we could not exist, at least according to the theory we currently have. Next slide. So there I am showing my spectrum, getting my diploma from the King of Sweden, which is a lovely party that they throw. It's now 2006, for a while ago. Next slide. There is the Great Hubble Space Telescope, and it has been used to check out this story of the expanding universe. It is still working beautifully, even though it is 34 years old. It was launched in April of 1990 on the space shuttle. I guess many people here remember that it was out of focus, and it took us a few years to get it fixed. And when it did get it fixed, we had a problem. We had so much beautiful data that the internet crashed when we were trying to release the pictures. At any rate, soon after that, we knew that the Hubble telescope, powerful as it was and is, was not enough to answer the questions of what happened at the very beginning. How did the first galaxies grow? So astronomers wrote a little book and they said, please build us another even more powerful telescope that can answer that question by observing infrared light. And also, by the way, on the side, start working on technology to observe exoplanets. It's planets like Earth, orbiting stars like the sun, where we, of course, we have a reasonable chance to discover life around other planets. I see a little conversation in the chat there. Is my sound coming through all right for most people?
It's fine, John. Continue.
Okay, thanks. So anyway, next slide. Here is the great James Webb Space Telescope as we picture it in outer space. You see the giant golden hexagon again, made out of 18 smaller hexagons. Of course, it's not solid gold. It's a very thin coating of gold on beryllium hexagons. Beryllium because it's extremely light and extremely stiff, and we're able to polish it well enough to get it up into space and make this enormous telescope, which is even bigger than the rocket. So the telescope is a joint international project of Europe, Canada, and the United States, and it includes 4 great instruments from the University of Arizona, from Europe, from Jet Propulsion Lab, and from Canada. So it's being operated now as the Hubble Space Telescope is from the Space Telescope Science Institute in Baltimore, Maryland. Next slide. There's the launch Christmas morning. It was perfect, which means that we didn't have to spend any extra fuel on adjusting the orbit. That's why we think we can have a good 20-year lifetime. Next slide. Here's where we put it. It's not to scale, this drawing. This is a suggestion or a hint of where the Lagrange point is. There are 5 Lagrange points where the combined gravity of the sun and the Earth will pull an object around the sun once a year. And we chose to go around the Lagrange point 2 because from that spot, the sun, Earth, and moon are all in one direction, and you can put up your one-sided umbrella, which I showed you already, to keep the telescope cold and in the dark. Next slide. Here is the scary movie of unfolding it in outer space, and it still is breathtaking to me to watch this movie. It worked perfectly. With all of the computer simulations that we had to do, and the rehearsals we did, Well, how did we get it to work perfectly? Well, we had 4 actual hardware tests of unfolding it. And then after it was folded up for the last time, we had a lot of time to get ready. So how do you practice with an observatory you do not have in space? We built a digital twin, a computer program that simulated most of the operations of this amazing telescope. So we would sit at the consoles and send commands to the digital twin and see if it did the right thing. And we still do that to make sure that when we're about to send a new command up to the telescope, that it will work as planned. So you can see it unfolding there. It's extraordinarily complex. And that means expensive. It also means powerful. There's the telescope. It's bigger than the rocket. When it's unfolded, it's 6.5 meters across, and the inside diameter of the rocket is 5 meters. So we couldn't do this science without this complex process, and we are thrilled that it worked. If you want to know how to make such a complex thing work, well, you practice out of town. You test and test and test and test, and you have review committees, and you have careful scrutiny, and you think about all the things you could possibly imagine where something could go wrong. And after you've done all that, then you have a chance to get it right. So we're still, although we did what we thought was the right thing, you still always wonder, have you really done the right thing? So there it is, it's working in outer space. I'll talk a little bit about why we observe infrared light. We have 3 reasons to observe infrared light. The first one is some things are just too obscured by dust. So the first thing you see here was a cloud where there's a star spitting out jets from its formation. And here it is in the second version of this, you say the same thing as seen with the infrared from the Hubble telescope. On the third one, we see cool objects, objects that are too cool to emit on their own visible light still can emit infrared. If you were out there in outer space, we would be able to see you thousands of miles away because you emit about 100 watts of power, and that's a lot. 500 actually, I misspoke, it's 500 watts. Third reason is that space is expanding, and that's what we say when we are trying to tell you that distant galaxies are going away. So we receive infrared light from objects that send out visible light, even shorter wavelengths. The wavelength gets stretched as the light propagates through the expanding universe. So next slide, or next button on this one. Here we see the space conceptually expanding. This is one of those weird things where we use a language about space expanding, but space isn't a thing. It's not a fluid. It's sort of empty, but not quite. So it has this crazy description that we say space is expanding, but actually all we know is that the distance between objects is increasing. Next slide. Our first data release just about 2 years ago, July 11th, President Biden put this out, and this is the picture of a cluster of galaxies in the middle, very big, fuzzy, bright objects, a handful of stars with the spikes sticking out of the images. And the things that are most exciting to us is the collection of strange-looking curved pink arcs out there, because those are magnified images of much more distant galaxies. The magnifying lens in question is gravity. Gravity operates by curving space-time. That means that light going past that big galaxy in the middle will be bent and focused. So when we get the image that we're seeing here, many of those galaxies have been stretched, expanded, even magnified by hundreds or thousands of times in places. So that's a very powerful tool, and it's still yielding great surprises. On our next slide, we have found that the earliest galaxies are, well, they're more than we thought there would be. They're bigger and brighter and hotter, and they seem to have grown faster than we expected. So is this a problem? No, this is a feature of the universe, and we just didn't expect it. It doesn't mean the Big Bang is wrong. It just means we didn't know how things could grow from the pink and blue blobs that I showed you earlier. How did those pink and blue blobs turn into these galaxies? It's a bit unknown, and this is a direct observational measurement that we have now to adjust our theories so they can fit it. Next picture. So they're also not round when they're formed. Quite often they are stringy things, as you see in these images. We shouldn't be too surprised because we actually have computer simulations that say this is a common thing. Nevertheless, it's wonderful to see the images. Next picture. We've even been able to visualize cosmic filaments in 3 dimensions. How do you see a cosmic filament in 3 dimensions? We need to take the map that's on the right-hand side. You see the objects of interest are circled there, and then find out how far away they are from us. And then you can get a 3-dimensional map that shows a stringy thing running through it. So this is presumed to be the result of gravity operating on those random pink and blue blobs in the very beginning, and it's still a wonderful surprise to be able to see it. So anyway, it's a thrill for astronomers. Here's another one. This picture shows a galaxy that's been greatly magnified by the presence of another galaxy with its gravitational lens. And here we see the arm of this galaxy is filled with globular clusters. If you're an amateur astronomer, you can go out and see some globular clusters that are local to us. Here locally, there are maybe 100,000 stars together, and they're beautiful to see in small telescope or binoculars. Here we see them billions of light years away, and we are so tickled to see this because we're looking back in time about, 9 billion years. So when we get to see that kind of information, we're beginning to learn how do the galaxies grow from the pink and blue blobs. Next chart. Here's an illustration that says once in a while, we can see a single individual star magnified immensely. Maybe it's a little cluster of stars, maybe it's a single star. This is called the sunrise arc. We found it. Its redshift is about 6, which means it was, we're seeing it as it was about 900 million years after the expansion began. And the curious thing about this gravitational lensing that I told you about, once in a while, the gravitational lens has almost unlimited magnification. 10,000, 100,000 is possible if you just, alignment is just perfect. So the big surprise is, once in a while, actually quite often, there's a star or a small cluster of stars that lies right exactly on that line, and we can see it. And so far, no big surprises about those stars. They're a lot like the ones we have locally, but all the same, the tool is so powerful that we are always being surprised by it. Next slide. Here is one of the most surprising pictures we've seen in a long time. Another gravitational lens, that big glowing galaxy on the left, and the box magnifies. What we're seeing here is 3 distinct images of a single most distant galaxy, and that galaxy has a supernova in it. And so we're seeing 3 separate images of the galaxy with its supernova. They're all a little bit different, so they tell you different kinds of information, and helping us see the details of very, very early galaxies. Next slide. Here is the picture of the most distant galaxy we have yet found. It seems to be born, we see it as it was when it was about 290 million years after the Big Bang. So how do you find these things? Well, you look at everything you have in your picture and you hope for the best. You hope to find a little fuzzy red dot, and then you say, well, that's interesting. What are the colors? Do the colors tell you that it could be extremely distant? And then you get a spectrum. You spread out the light with one of our instruments to see if it actually behaves as it should. And the telltale sign is absorption of the shorter wavelength light by intergalactic hydrogen atoms. So what we see is a spectrum that's very smooth and simple, and then it cuts off very abruptly at that particular wavelength. And that's a direct measurement of the cosmic redshift of this object. So as this is as far as we've gotten so far, there are probably more objects to find, but we have to be lucky to find them. So we have to study a lot of sky to find these very rare objects. Next picture, please. Now, coming back to some that are a little more local but beautiful to look at, this is called Stephan's Quintet. There are 5 galaxies in the picture. The one on the left is quite nearby, and you can actually see individual stars in the image if you actually had the image itself instead of only computer presentation. The other 4 are in the process of colliding together, and the big splash is making formation of new stars. You see the pink arc right there in the middle. That's heavily excited gaseous material has been caused to generate new generations of stars, and they're lighting up. So that's what we're seeing there. The top one has a black hole in the middle. And so how do you know that? There's something that's much brighter than it should be, just to be an ordinary light source in a galaxy. And so it looks like a point object, but it's much too bright to be an ordinary star. So it's a black hole where stuff is falling in, being heated to extreme temperatures, and then we can see it. Next chart. This is another very picturesque one. It's called the Cartwheel Galaxy for obvious reasons. A galaxy went right straight through the middle of the big one and sent out a splash. So it caused a new generation of stars to be formed in the gaseous material that is being flung out from the center. So did something like this happen to our own Milky Way? Quite likely, although the traces are long past gone, and so we can't tell that kind of thing today. On the other hand, it's not so unlikely this could happen to our other galaxies and may have happened to ours. Next picture. Here's a galaxy with a hole in it. Actually, most galaxies have holes in them. What we're seeing is a hole in the infrared emission. And the infrared emission is coming from dust clouds mostly. And why is there a hole? Now, there is a hole, and each of these holes is an inflated gas bubble. When stars are born, quite often they're so bright that they send out so much energy, they vaporize everything that's left, and they push away the remaining gas in the neighborhood. So this is inflated in a way very similar to what inflates a sponge, and you get a kitchen sponge, it has holes in it because of the gas pressure. So from this, we're beginning to learn how stars are being born today. Next picture. This is a direct image of stars being born today with a lot more detail in it. This is called the Pillars of Creation, and it looks very different when we use the Webb telescope as compared with the Hubble, because now the Webb telescope is able to see inside the dust clouds and see individual glowing stars as they are beginning to peek out from the dust cloud. Where you see there's a wind blowing here. The wind comes from previous generation of stars. And just as I was telling you about the galaxy with a hole in it, there's a wind because the gas is flying through space at huge speeds. And it's changing the shape of this cloud, evaporating the surface, and causing new generations of stars to be born inside. So inside this cloud, there are thousands of new stars being born. Some are being, we can study directly. If they were closer up, we might even be able to know if they had planets. Next chart. This is a map showing a whole galaxy with soot coming out, where the technical term is polycyclic aromatic hydrocarbons. These are produced when stars get old. They release the carbon that's been formed inside them during nuclear reactions, and that as that comes back out into space, we see these compounds. They emit at certain particular wavelengths, and it's fantastic to be able to see the shape. So these are called galactic fountains because the material is being spit out up and down from the plane of the galaxy. We can begin to do chemical analysis on the intergalactic and interstellar medium in these galaxies, and by now we have well over 100 different molecules have been identified in space, not in atmospheres of stars or planets, but in actual space between the stars and planets. Next chart. Here is a big surprise. This is not a total surprise that this object is there. This star blew up in 1987 as we saw it, and we called it a supernova. It's in a Large Magellanic Cloud in the southern hemisphere. Now with the James Webb Telescope, we're able to expand the image and see that not only Does it have this amazing structure with a ring of luminous dots, little jewels, in the material that was spit out by the exploding star? We can even begin to do chemical analysis, and we see argon in the material around it. And we can even see the central object there. There's a neutron star. So when a star blows up, the different things could happen to the debris. Once in a while, a black hole is formed and everything falls in. Sometimes a black hole is formed and some things come out again. Sometimes a neutron star about 10 miles across is left, and that's what we see here. Quite often spinning very rapidly with extreme magnetic fields and sending out pulses of radio as well. Next chart. Here is a surprise. This is not from the Webb telescope itself. This is a location of a black hole, which is not seen. This is deduced from Hubble measurements of the stars in the neighborhood of that little black circle. We've been watching this area with the Hubble telescope for long enough that we can measure the orbits of stars zipping around that black spot. And we can use that then to calculate the mass of the object in the middle. And it's called an intermediate black hole. It's much larger than a single star, which is 10 or 100 solar masses, much smaller than the mass at the center of a large galaxy of millions or billions. So this is in between. So this is beginning to tell us something about how the great black holes are formed. Next chart. Here is a new star being born, and as we have talked about before, often we see jets coming out. What we see here is a dark zone right there in the middle. It looks like a fur ball of some sort orbiting around the star. We're looking at it edge on, and that's material that's full of dust, and it's on its way in towards the center. As it falls in, it is heated, and the star is spinning very rapidly, and it is sending out jets of material from its north and south poles, and that's a very typical phenomenon in astronomy, a growing spinning object squeezing out jets from its poles. A new star. Next chart, please. Here is a new star with planets growing in it, probably. This is a slightly advanced version of the one we just looked at. The dust cloud is less opaque, but you can still see that you're looking edge on into the new solar system. Here, that little thin line across the middle of the hamburger is probably the dust cloud concealing tens of new planets, some of which will stay in this new solar system, and some of which will be expelled back out into space. By the way, we now know that most stars have many planets, and that there are many planets without stars that have been expelled, presumably from new star systems like this. Next chart. We have found that some of those objects out there are actually the size of Jupiter, but they don't have a planet, a star around them. Sometimes they come in pairs. So this is a big surprise. We see them in the Orion Nebula. In the next chart, I'll show you another beginning of things about planets around other stars. We knew when we set off that we would be able to do this one trick, waiting for a planet to go in front of the star. This happens, we can now observe the light that goes through the atmosphere of the planet on its way to our telescope. When you analyze that enough, you can determine the chemical analysis. So how do you do the chemical analysis of a planet? Well, each different molecule absorbs or emits light at different wavelengths, and so we spread the light out into a spectrum, measure the intensity of different wavelengths, and that tells us the chemistry. We've been doing that for generations. We started with the sun and discovered the element helium on the sun that way, and now we can do it on distant planets. Next chart. Here's an example. This is a big, fat, hot planet, and it has sodium, potassium, carbon monoxide, carbon dioxide, water, and even sulfur dioxide in its atmosphere. And this is a planet you would not want to live there, but is big and hot. The next chart now. This is a record of a planetary collision or something. There's a star called Beta Pictoris, the second brightest star in the constellation Pictoris, or the Painter. A few years ago, the Spitzer Space Telescope observed the spectrum of this object, and then we looked at it again with a Webb telescope, and it had changed. The conclusion we draw is that there was a collision between asteroids in this system, producing a whole set of dust at a particular distance from the center, and therefore that it had a particular temperature and chemical composition. And we can see that it has changed. So some year we may be able to see much better inside this. It's a very bright cloud of dust. Next chart. Here's another one. This is what we call a hydrogen ocean world, or a Hycean world. And we've been able to measure the constituents, and we've got a lot of water in there. This is a planet we calculate it's big enough to hold water and hot enough to have the water be in the form of steam over an ocean. So there's that one. Next chart, please. This one is a planet that's hot enough to have sand grains in the atmosphere. So definitely you would not want to live there, but this is something we can measure with our technique. Next, yes, here we go. This is a really new measurement. There is an object about 6 times the mass of Jupiter that is shining separately from its own star. One of the few cases where we actually have a planet bright enough to see despite the brightness of the star next to it. This is a star is called Epsilon Endis, and epsilon means it's the 5th brightest one, is the 5th letter of the Greek alphabet. And A means the star is a binary, and then the little b means it's a planet orbiting around that star. So yes, we got a picture of a planet. Next chart. The solar system. Here's good old Jupiter with its red spot, and which is becoming even more interesting. But let's look at the next pictures coming along, because we have imaged all the great planets out there, the great ice giants, and all of them have rings. Here's a surprise to me. We have measured the presence of hydrogen peroxide in Ganymede. Ganymede is a satellite of Jupiter. We believe that it's pretty cold, but it has an ice-covered ocean. And now we have hydrogen peroxide on the surface. How do you explain that molecule? Well, that's not easy. But the chemists are busy trying to tell us how that could happen. We've even seen a carbon dioxide atmosphere around the planet, the satellite Ganymede. And how do you see this? Well, in both cases, you look at particular wavelengths where you know that they came from that particular molecule. And then in this case, you can even map to see where they are on the planet or around the planet. Next chart. Sulfur dioxide. Who'd have thought you'd be able to see sulfur dioxide on Io? Io is the innermost Galilean satellite orbiting Jupiter, and it is so hot from tidal heating that it has molten sulfur volcanoes. That's interesting. We knew about that a long time ago from the flyby way back in the previous millennium. Now we're able to say we identify the molecule sulfur dioxide. We can see where it is on the satellite, and we even can measure the temperature of the surface of that. So this is a combination of surface maps that were made when we visited with the temperature and molecule maps we made with the Webb telescope. Next chart. We are going to go have a closer look at Europa and the other satellites of Jupiter. The Europeans have launched their Explorer satellite, the Jupiter Icy Moons Explorer. It's supposed to arrive in July of 2031, and it will orbit close to all of the icy moons of Jupiter, getting pictures, radar data, other information that will tell us about the inside composition of those satellites. They're all interesting. This one is Europa itself. This one shows that there's carbon monoxide on the surface, and we can see it at different wavelengths. And it's not always in the same place at the same time. So remarkable ability to spread out the light, observe a particular molecule there. We are going to go have a closer look with this satellite. I'm not sure if it shows correctly on your screen. Yes, anyway, there it is. The Europa Clipper is to be launched October 10th, next week. And it will arrive in 2030, and it will go orbiting directly around Europa itself. Get a really close look. This is a place where there could be, we hope, signs of life, because water is coming out from the cracks between the ice blocks on that little satellite. And that water could have organic molecules in it, and that would be an extraordinary discovery. I think last time I talked with you, we had already done this experiment, but we have attacked an asteroid. This one was a double asteroid, and we hit one of them with a chunk of metal. And here's the Hubble and the Webb telescope both observed the collisions. So this is getting some of the basic information about how to deflect an asteroid that might be coming towards Earth. Next chart. Here is another extraordinary object to look at. This is Titan. Titan is the satellite of Saturn. It is so large that it has its own atmosphere. And we've been observing its spectrum with the Webb telescope. We get the weather and the clouds. This satellite of Saturn has liquid rain. It has methane and ethane rain. It has clouds. It has lakes and rivers. And it will have a helicopter. In 2034, our helicopter will arrive there and will begin hopping around from place to place to examine the details of the surface, see if it's similar everywhere, which is probably not, and to begin to observe what I suppose we should call titanology, the surface rock and composition of Titan. If logic tells us there could be any other alternative besides our modern water-based, carbon-based life forms, this is nature's experiment. Here is the big old Uranus, the one planet in the solar system where the spin axis is almost in the plane of the orbit. How did that happen? We do not really quite know, but it could have been a collision with some other object that changed the spin direction. At any rate, here it is with its beautiful ring of objects around it. So to conclude this part of the talk, we have a picture of what will happen to us in about 4.5 billion years. The great Andromeda Nebula will collide with our own Milky Way, and we will not be here then because that's about the time that our own sun will be swallowing up the Earth. We have about 1 billion years to go before the sun is too bright for us and we need space travel. But after 4.5 billion years, we really have to dodge. So this, of course, is the simplest version that you could do with Photoshop, but it is something that will happen to us. So I have talked very quickly, but I think I've given time to ask for questions if people have them, or I could go on and talk some more about the future of what we can do next.
John, why don't you spend a few minutes on what happens next on the Webb schedule, and then we'll get to questions. We have time.
Okay, well, I'll talk about what do we do with the Webb telescope? How do we decide what to look for? Well, every year we send out a call for proposals to astronomers, and we got 2,000 proposals. So then we get a committee to read the 2,000 proposals, and then we say, okay, you and you will point the telescope at your target. And that's how we decide what to look at with the Webb telescope. But now we're showing on the screen what happens next in other missions. This is the Euclid mission, which was launched last year, SpaceX rocket. This is designed in Europe to look for evidence of dark matter and dark energy. The next slide shows you our American mostly project to survey the entire sky. And it's about to start operations in South America. It has a totally gigantic telescope of 8 meters plus across, 3.2 gigapixel camera, and it will take a picture of the entire night sky every 3 nights. They expect to see about 10 million things change every night. So we will need some wonderful computers and some wonderful people to find out what is important about that. By the way, notice that it's named for Vera Rubin, who was one of the pioneers here at in DC for measurements of the cosmic dark matter. And the next one is named after another brilliant woman astronomer, Nancy Grace Roman. She was the head astronomer at NASA headquarters for a long time. And this telescope is going to look for the dark matter, the dark energy, and also look for planets around other stars. We're carrying a coronagraph capable of seeing a little dot orbiting next to another star. Probably not quite good enough to see an Earth orbiting around a star like the Sun, but we're going to try and see what it can do. Then the long-term plan for NASA is, let's build an even bigger telescope than that, about as big as the James Webb Space Telescope, but more like the Hubble telescope on steroids. So bigger and much more perfect, capable of seeing a little planet like Earth orbiting a star like the Sun. So that's what we're doing next that we know of. And many more things are in plan. Okay, let's talk about a few questions.
Thanks, John. We have a few already. So let me first pass on one from Ann Finkbeiner, who is one of our frequent visitors to our Science and Society. So she has a question about those mysterious stringy galaxies that you showed wonderful pictures of.
Yeah, so
she wanted to know, are we looking with those images edge on to the spirals, so you see the knots are forming stars, or are they stringy from any perspective?
good question. That was a hard question the original authors had to answer. How do you know that you're not just looking edge on at things? And the answer is, when you look at this distance back in time and out in space, they're all stringy, they're all straight and irregular like that. None of them are round. So that tells us that they're not flat things edge on, they are actually stringy things.
Thanks. Richard Schwab would like a few more details on how we get such distinct chemical analyses from the measurements from the telescope. You identified distinct chemicals in the atmosphere of small satellites to galaxies. How is that done in some next level of detail?
Yeah, okay. Well, we have spectrometers on board, so we can spread out the light of a star or a planet or a satellite or a galaxy into its constituent wavelengths. How bright is it at each different wavelength? So each molecule or atom has its own special wavelengths. When you go to the rocket performance on July the 4th fireworks, each of those bright colors that you see is a specific wavelength coming from a particular chemical element. So we look for those patterns out there in the sky, and when we see those patterns, we say, oh, it's a particular wavelength, that means it's a particular atom or a molecule. Of course, we do have one thing we have to figure out too, which is the object coming toward us or going away from us? Because that also changes the wavelengths that we see. So if we see, say, a set of wavelengths that are all related in the same way, different multiples of each other, and we see that same pattern in a distant object, we can simultaneously determine the chemical composition and the speed of motion toward or away. We have instruments on board that can actually spread out the light into thousands of different wavelengths, about 3,000 different wavelengths for each one. So that's a lot of detail that tells us very clearly what molecule we're looking at.
Thanks, John. What is the heaviest molecule that have been identified from Webb observations so far?
Of the ones that I showed you, it would be sulfur dioxide, because that's the three heavy atoms that we in our list. But we know there's a lot of heavier stuff out there. I think we've actually observed buckyballs, carbon with 60 atoms. Those are harder to identify, but seem to be pretty common in what I call the polycyclic aromatic hydrocarbons, or the soot that comes out from galaxies. We see those molecules, and they have a characteristic set of wavelengths, so we're pretty sure they're there.
So one of our readers has been checking the journal Nature Communications, and it noted that the Webb has seen traces of carbon dioxide and hydrogen peroxide on Charon. You mentioned those. So, from your own view, do you think the collaborators of astronomers and cosmologists have been surprised how much we've learned from our own solar system as opposed to deep in the cosmos?
Well, I was surprised. I showed you these beautiful maps of the molecules on the satellites in our solar system. I had no idea that was possible. So that's because I was thinking about it in advance, but somebody thought about it and said, we should look over there with this tool, and that'll be just what we need, and we'll find something. And sure enough, they did.
So you've mentioned a number of things that were surprising, particularly the appearance of young stars and galaxies just 300 million years after the Big Bang. What is on your list of most surprising things that you have seen from the Webb observations?
Well, in some ways, I'm just surprised by how beautiful the pictures are. People asked me 30 years ago, would the pictures be beautiful? And I said, yes, but how did I know? So then I'm really pleased to see we're getting some more information about the dark matter and especially the power of the gravitational lens technology and technique that I showed you. We knew it would be powerful, but we did not know what it would show us. And we just don't have the imagination to try all the calculations you could do to predict everything. And so seeing how much there is to find is just a thrill to me. So my successor on the Webb telescope is Jane Rigby, and that's one of her specialties.
So we have a follow-up from Anne. It's again about the string of galaxies. So galaxies form not as blobs, but as strings, long, narrow strips. Are the stringy galaxies really clouds of forming stars strung along a filament of gas? How would you describe the images of stringy galaxies that you were showing us?
So I guess we're really looking for the formation story of those objects. We have numerical simulations of the formations of galaxies, and even from 10 or 20 years ago, they're beginning to show this kind of structure. There's a simulation called Illustris, and people simulated a volume of space starting with the random blue and pink and blue blobs and propagating forward in time with hydrodynamic equations and everything they knew. And they got stringy things like that. So I think it's the natural result of gravity more than it is magnetic fields. But then when we get down to the smallest scales, the magnetic fields become larger and they start to control how stars are born. We do have evidence that the magnetic fields control how stars are born in groups, that a whole bunch of stars will all be orbiting in the same direction and lined up along magnetic field lines. So that's something we're beginning to understand. But her question is one of our tough questions.
John, this is Ray Wise. Can you hear me?
Yeah.
The lovely talk you've given, absolutely beautiful. But I have a question. How far back in time, or to what value of Z do you think WJST can look for the first stars? I mean, I noticed that in their talk, you had an object at 15 or 14.7 Z, which I think is remarkably deep. And there are already stars at that distance. A very interesting question to all of us is, when do the first stars show up? And can JWST tell us something about that?
Yeah, so of course the thing I showed you isn't very big and very bright, but it's and so it's hard to analyze it much. Um, what we know of it so far is that its spectrum is almost featureless. That is to say, it's got the characteristic drop due to absorption from intergalactic hydrogen and almost nothing else, which means it's these are very young, these are stars which are made out of mostly hydrogen and helium.
Yeah,
So
but
that's
can
a sign that they really are among the first generation. On the other hand, our big question is, well, how fast does it take for this to get started? Because a typical very massive star will only live for a few million years and then it goes poof, and its
yeah.
material comes back out into space. So within only a few million years, the first stars will have polluted the neighborhood with heavier elements. So this is an interpretive process as much as it is an observational one. We're not going to get a whole lot more information than the spectrum that we have.
Uh-huh. Well, thank you. This is really a wonderful demonstration of an incredible idea that you had. Thank you.
Yes, well, thanks. And by the way, I shouldn't say it was my idea alone. And my entire committee wrote a book saying we should build this.
Yeah, I
And
know
then,
that, but you were the
yeah,
guide. Come on, don't give me that.
yeah, thank you, Ray. I was the guy who was called on to make it happen.
Yeah.
Yeah. Now, I want to remind the audience, we don't usually take questions from the audience, but you just heard two Nobel Prize winners talking to each other. We had Ray Weiss here a year ago talking about LIGO, the wonderful experiment that he spent 50 years on that detected gravitational waves. And Ray was my mentor when I was a student at MIT. He was also John's mentor as he was first starting on the COBE project, which gave him the Nobel Prize. So welcome to the audience, Ray. Thank you for chiming in.
Okay, thank you for having
Yeah,
me.
thank you, Ray. It's great to see you.
So we are at the end of our allotted hour. We want to thank John for coming back 2 years into the Webb mission. You were informative as usual, but the pictures are just spectacular. And I want to remind the audience that we have recorded this talk, and it'll be up on the Lewis Library YouTube site not too distant future. So you can go back and admire some of these wonderful images that John showed us today. And I want to remind you that the next talk in this series is not Tuesday, first Tuesday of the month, because we'll all be voting. But on Wednesday, November 13th, we will have a talk called Into the Great Wide Ocean by Professor Sankey Johnson from Duke University. And rather than going up into the sky, we're going down to the ocean. So we posted that on the chat, and we welcome you back a month from now. And we thank John, we thank Ray, we thank all of you for tuning in tonight. So I'm going to ask Rebecca to open up everyone's microphones so we can thank John for his talk tonight.
All right, everyone. So feel free to go ahead and unmute yourself and say thank you, and go ahead and give your applause.
Thank you.
Thank you.
Thank you.
All right. Also, thank you. I just want to give a quick thank you to Linda Dilla, who was doing the slideshow for us. We had a few technical difficulties right at the beginning, and Linda jumped in, downloaded a very large PowerPoint presentation, which probably broke her computer, and did the old-fashioned next slide, please. So thank you, Linda, for stepping in and doing that. So thank you, everyone, for joining us, and we look forward to seeing you next month. We'll see you then.